This video is about section 6-3, the central limit theorem. What we looked at earlier in this chapter assumes that the data is normally distributed. Lots of things are normally distributed. I list some examples there. Heights of men in the U.S., heights of women in the U.S. Lots of things, unfortunately, are not. If you look at heights of people in the U.S., they're not, because the means and medians of women and men don't match up. So what the central limit theorem does is it allows us to apply the power of the normal distribution to things that don't start out normally distributed. And statistical process control makes extensive use of this. Statistical process control is a component of and a forerunner of Lean Six Sigma. So to demonstrate what the central limit theorem actually does for us, I have a simple example here, and you'll see these graphs in the notes. If we start out with rolling a single six-sided die, we have six things that could happen, all of which are equally likely. So we have this flat as a tabletop graph, which looks nothing like a normal distribution. Now, if we roll two dice and add the totals, you'll see there's only one way to get a 2, there's only one way to get a 12, there's 6 ways to get a 7, and you'll see we have sort of a triangle shape here. So certainly it's not normal yet, but it's certainly a little different than what it was at a single die. Go to 3 die, add them up. Well, now there's only one way to get a 3, only one way to get an 18, but in here the 9, 10, 11, and 12, there are lots of ways to get it. And you're starting already to see a nice shape there. Add a fourth one. Again, only one way to get a 4, only one way to get a 24, lots of ways to get these numbers in the middle. Get to a fifth one. What you see is, as you start grouping data, it self-normalizes essentially. When you pull a random sample out of data, even if the underlying data is not normally distributed, the mean of the sample, they will be normally distributed. So, if you get a large enough sample, which to be technically, statistically significant is a sample of 30, then these means will essentially follow a normal distribution. Now, while that's to be ideally statistically true, as you can see from this graph, it is possible in the real world that you may try it with smaller subsets. I can assure you that when I worked at Johnstown Corporation years ago doing this, we did some very expensive parts. We couldn't wait for 30. We used subgroups of 5. Even though it wasn't purely statistically correct, it was practically significant. Because, and you'll see here, it should be reasonably normal. To get a very low number or a very high number is very unusual. All right, so the central limit theorem says, as sample size increases without limit, the shape of the distribution of the sample means, taken with replacement from a population with mean mu and standard deviation of sigma, will approach a normal distribution, which is what I just showed you in pictures. And we could continue that progression that I had shown 1 through 5. Now, things to realize. The central limit theorem is used when you were looking for information about a sample mean. What we had looked at earlier was for individual datum points. So if you think back to example 10, we were looking at what is the probability of getting a result on one single day. These types of problems, we're looking for a sample. All right, and here's where. For the central limit theorem to be applied to the original data to be normally distributed, or the sample needs to be 30 or higher. As I mentioned a few minutes ago, the caveat, this is absolutely statistically correct. Practically, you may see much smaller groups. All right, now the difference in calculation is relatively small. When you're calculating the z-score in this case, the numerator, instead of being x minus mu, is x over bar, which is the sample mean, minus mu, the population mean. The denominator, instead of just being the standard deviation, is now the standard deviation divided by the square of the sample size. So if we look at example 11, kindergarten students have heights that are approximately normally distributed about a mean of 39 inches with a standard deviation of 3.0 inches. A random sample of size 36 is taken and the mean is calculated. What is the probability that this mean value will be between 38.5 and 40 inches? Okay, now the key determination here, we are not looking for the probability of a single kindergarten student. We're looking at the probability that a random sample of 36 students is in this range. All right, so if we look at it, this example, our z-score formula says we're going to take the sample mean. So we'll do it first for 38.5. 38.5 is our proposed sample mean minus our mu, 39, divided by the standard deviation, 3.0, over the square root of the sample size. So do the subtraction in the numerator. This, when you have a fraction like this, that changes the rules of algebra a little bit. We need to treat the numerator as a unit, then the denominator as a unit, and finally do the division. So 38.5 minus 39 is negative 0.5. Square root of 36 is 6. 3 over 6 goes to 0.5, so we have negative 0.5 over 0.5. Our z-score for 38.5 is negative 1. Now, if we calculate the z-score for 40, which is the top of our range, 40 minus 39 over 3 over the square root of 36, we end up with 1 over 0.5. We get positive 2. So, our probability that the mean falls between 38.5 and 40 is equal to the probability that the z-score is between negative 1 and 2. So if we dig out of the z-table or use Excel, the probability to the left of z equals 2.0 is 0.9772. The probability to the left of negative 0.1 is 0.1587. So the area between those two is the difference, 0.9772 minus 0.1587. So the result is 0.8185.